Okay, we're starting Unit 3. We've successfully completed Unit 1, which was rational numbers, powers, and polynomials, and Unit 2, which is our big graphing unit. It's our really important unit. So now we have a small unit that's going to take a lot of what we learned in Unit 2 and apply it to real life situations. So we're going to investigate relationships between variables when we're kind of working from real life data and real life numbers. And so this unit has a lot of vocabulary to it. So today's lesson is really just going to be an exploration of that vocabulary and how we're going to use it. So the very first thing we're going to talk about is scatter plots. That's what this unit is about, as opposed to those nice linear graphs we did last unit. We're working with scatter plots. So a scatter plot, here's an example of one. You'll see that the data is kind of scattered on the graph, and that's a scatter plot. So you can see right here, that's a scatter plot. So this is the type of graph that we're going to be using. And what it is, it's real measured data. So each of those data points is an actual measured data point from a real world situation or from a really good simulation that's taking into consideration the variability that happens in the real world. So when we're working purely mathematically, we have these data points that line up beautifully, but in the real world, there's lots of different things that are affecting our data when we measure it. So we never see these absolutely perfect graphs. We see graphs where there's some fluctuation in the data, there's some variability in it, and we have to then determine what kinds of relationships we're looking at between the different variables. So you can see this graph is about the distance to destination when you're flying on a plane and how much it costs to travel there. So they are asking us, is there a relationship between how far you're traveling and how much it costs? So when you look at this graph, what do you notice? Would you say there is a relationship? So let's look back at some of our vocabulary. We've got scatterplot. We know what a scatterplot is. So let's look at independent and dependent variable. So the independent variable is always on the x-axis. And it's the one that we think is kind of controlling the data. So we would say this is the cause of the relationship. Okay. The dependent variable is always on the y-axis, and this is kind of the result of the relationship. So let's look here and see if we can figure out which one is independent and which one is dependent. So when you look at this, you say, okay, what is going to cause this relationship? Is the cost going to determine how far you go, or is it how far you go that determines the cost? So I think we'd all agree that it's how far you go that determines the cost. So this one is the independent variable. And this is the dependent variable, right there. Independent variable, dependent variable. Notice again on the x and the y, just like we said. So let's take a look. So we've got independent and dependent. Well, we're going to jump here. We're going to look at positive and negative. A correlation is this idea of a relationship, that they are moving somehow related to each other. We call that a correlation. So a positive correlation would mean that they're both increasing. So we look at as x increases, my apologies, that should be back in just a second. There we go. As x increases, y what? So for the correlation, as x increases, what happens to y? In this case, when we look at the graph, we could say, okay, as x increases, so as we move to the right on the x-axis from 0 to 500 to 1,000 to 1,500, we'd say, okay, as x increases, y is also increasing. Not yellow, not yellow, orange. Increases. This would mean it is a positive correlation. And if you think back to Unit 2 that we just finished, you might realize that a positive correlation and a positive slope look a lot alike. So let's think what a negative correlation is going to look like. Okay, so if we have as x increases, y decreases, that would be a negative correlation. Okay, 2 R's. And that would kind of go in that direction. That would be a negative correlation. So positive and negative, again, very similar to the slope ideas, but sometimes you won't have a line. This graph has a line of best fit. Sometimes you won't have that, and you'll just look at the data points and you'll say, okay, they're in general moving up to the right, or they're in general moving down to the right, and that gives me the idea of what if it's a negative or a positive correlation. So we've got those done. Okay. A strong correlation and a weak correlation. These have to do with how close the points are to a line or curve of best fit. So how close the points are to a line or a curve of best fit. So you see this line here. I'm going to highlight it for you. That's a line of best fit. That is a line that splits the points really evenly. So you'll notice that there are, I'm going to change this color. Okay. 1, 2, 3, 4, 5, 6, 7 points above. And 1, 2, 3, 4, 5 points below. So those should be split pretty evenly. So ideally we'd have 6 and 6, but sometimes it's impossible to get a line to split them that evenly. And the other thing to notice is this distance from the line here. You should try and minimize those distances from the lines. So the line of best fit, by splitting the points and kind of averaging out those distances, is the best estimate of the relationship between the variables. So the line of best fit is really, really important because it gives us an idea of what the true relationship between the variables actually is. So even though there are things in real life that make those data fluctuate, that line of best fit is trying to control for them and give us an idea of what the actual relationship behind the scenes is. So when you have that, this is here, this is the line of best fit. When you're looking for strength or weakness, it's about how close they are to the line of best fit. Not how close they are to each other, but how close they are to the line of best fit. So these ones in general aren't that far away. So when you look at these distances here, they're not that far away. This would be a relatively strong line, strong relationship. If we had points that were like this, all over the place, we'd say it's a very weak line of best fit or a weak relationship. Okay, so we've got line of best fit, strong and weak. Oh my goodness, we're almost getting through all the vocabulary. So linear and nonlinear. We should know this again from Unit 2. If you're going to use a line to describe this, like we have here, then that is linear. So this would be a linear relationship. A linear relationship is one that is best described using a line of best fit. We could also use a curve of best fit. So if we had data that was going, putting some extra data points on here, like that, we would use a curve of best fit to describe it. And we would say that the relationship is nonlinear. So in this case, what we have here is a positive, strong, linear relationship. Okay? A positive, strong, linear relationship. That brings us to our hypothesis statement. And the hypothesis statement is a statement of the relationship between two variables. Okay. There we go. A statement of the relationship between two variables. So I'm going to write a statement of the relationship here, looking at this. So I'm going to write my hypothesis. And I'm looking at this, and it's almost the same as the statement that we have for deciding whether it's positive or negative. So I'm going to write a statement involving the independent and dependent variables. So as now I'm going to put in the independent variable, which is distance to destination. So I just label it distance to destination increases. We always state it as this increases, the dependent variable, airfare cost, does what? The airfare cost increases. That's the hypothesis. I've basically taken an educated guess on whether or not it's going to be a positive or negative relationship. So a hypothesis for a linear relationship can be stated really simply. You say as the whatever the independent variable is increases, then the dependent variable and what you think it's going to do is going to increase or decrease. Okay. The only other terms we have on here are interpolation and extrapolation. And interpolation and extrapolation are skills we will use in this unit. We're going to use them in a couple different assignments. And what they're doing is basically trying to figure out data points that we didn't actually measure. So if we look here, there's nothing measured at 1,250 miles. So if I say right here is 1,250 miles, and I want to know approximately how much a trip that's 1,250 miles is going to cost, I would say, oh, there's 1,250 miles. I'm going to go up, and I'm going up to the actual line. That's my line of best fit. Remember I said that was an estimate of the true relationship. So I go to my line of best fit, and I'm going to come across, and I'm going to say, okay, so at 1,250 miles, it's going to cost maybe $220. And of course, on grid paper, you'd actually be able to make a much better estimate than the one that I just did. But we'd say, okay, so it's going to be about $220. That's called an interpolation because it's within our data points. If I said 1,600 miles, you can't see that. There you go. If I said 1,600 miles and went all the way up the outside here to there and across and said that's about $260. I don't need the $sign because that's in the description. Okay, $260. Then I would be making an extrapolation because it's outside of the data. So this one is an interpolation. That's a estimate inside